In the world around us, a wide variety of things are happening. Some of them are more significant to us, while others do not interest us. By selecting noteworthy events that matter to us, we change our behavior and switch from one task to another. So how does the selection of these significant events take place? What neurophysiological processes are at the basis of these actions? All of this will be covered in today's lecture, which is focused on the event-related potential P300. To understand the P300 phenomenon better, let's look at a situation that is fairly typical of everyday life. Imagine that you're a bird photographer who takes pictures of birds in a park. Although there are many different types of birds in the park, you're only interested in one that is rarely seen, a coal tit. You don't need any other tits. So you only press the camera button when a coal tit shows up. In any other situation, you take no action. Let's take a look at how this happens. Let's now examine the situation from the perspective of the P300 registration paradigm. Overall, we observed 9 tits and 1 pigeon. Most of the time, gray tits flew in, and there was no need to react to them. This is recognized as a standard stimulus. A coal tit flew in twice. This was the target stimulus, a rare target stimulus that required you to press the camera button. And once a pigeon flew in, which was an entirely unexpected stimulus that was new to you. This stimulus will be referred to as a distractor because it distracts the subject's attention. The stimulus presentation order we are talking about is called the oddball paradigm. We will now examine this paradigm's application in laboratory conditions in more detail. To register P300, we can use stimuli from any modality. It could be auditory, visual, or tactile stimuli. It's essential to select a pair of stimuli that are slightly different from each other. For example, we can use visual stimuli, colored circles of blue and red, that we would alternately display to the participant on the computer screen. If we present these stimuli equally and without providing the participant with any instructions, each of these stimuli will elicit a distinct sensory response. When the brain responses to blue and red circles are averaged, we get the typical visual evoked potentials. But if we adjust the probability of presentation, making one of them presented much more frequently, say a blue circle, and the other much less frequently, and we give our participant a specific instruction, he should somehow pay attention to this rare target stimulus, for example by counting it to himself each time it appears, or by pressing a button when it does, then the situation will change dramatically. When we average the brain responses to the blue circle, we will get the identical sensory potentials that we got the first time. When averaging responses originating from a target stimulus, the red circle, in addition to the sensory evoked potentials, after 200 to 150 milliseconds, we will notice that a strong positive wave will begin to form in the averaged potential, peaking around the 300 millisecond range. This will be P300. The distinction between average responses to target and non-target stimuli is especially clear when one response is subtracted from another. Similar sensory components are leveled in this situation, while cognitive process-related components are retained, such as identifying of a target stimulus, which is linked to working memory and making a decision that the stimulus needs to be responded to. All of these processes require heightened attention, which is believed to be provided by neural inhibition. Because neural processes are inhibited, all unwanted extraneous processes are slowed down, allowing one to focus more clearly on the task at hand. P300 amplitude correlates to the number of neurons engaged during the cognitive task, while peak latency indicates the speed of event processing, the speed of categorization of a significant stimulus selection. The shorter the peak latency is, the faster the participant completes the task. What are the mechanisms of P300 generation? To make sense of this, let's examine the P302 subcomponents, P3A and P3B. These subcomponents differ from one another by their origin and their topography. The P3A subcomponent is an earlier component that is connected with hippocampal and frontal lobe activation. While looking at average responses, we'll notice this component in the frontal and central leads. The P3A subcomponent is best detected in the three-stimulus paradigm, where the distractor appears alongside the standard and target stimuli. The participant is not told about the appearance of the distractor, thus it's a completely new and unexpected stimulus for him, resulting in an orienting response. The beginning of the orienting response is accompanied by the appearance of P3A. It is confirmed by the fact that the P3A amplitude decreases when the distractor appears many times. The P3A is believed as a result of attracting attention to a new stimulus to resort to working memory, where representations of the presented stimuli are stored. Later, under attention control, memory storage is accessed, and the parietal and temporal cortical areas are activated. As a result, a later P3B component with primarily parietal topography is generated. The P3A and P3B subcomponents are associated with different mediator systems. The P3A subcomponent is mostly related with the dopaminergic system. This is supported by the observation of P300 deficiency in patients with Parkinson's disease, a disorder marked by dopamine shortage. Along with the dopaminergic projections, a certain role in the generation of the P3A component is assigned to the anterior cingulate gyrus, which enables the attention to shift from one object to another, and the neurotransmitter glutamate. It has been shown in an experimental model that when a monkey is given ketamine, a medication that blocks glutamate receptors, the animal's amplitude of P3A decreases significantly. The later P3B subcomponent is more associated with the noradrenergic system. Now that we've explored the mechanisms of P300 generation, let's try to answer the question: can we solve the opposite problem and discover which of the objects our participant is interested in based on the change in the potentials? The answer is yes. This technology has been used successfully for many years in brain-computer interfaces, which employ the P300's potential to operate various external equipment like a patient chair, a manipulator, or a typing device. In brain-computer interfaces, all of the commands from which the patient can select are displayed on the screen at the same time. The commands are then highlighted one by one, and the patient, having picked the command that he requires at the time, somehow marks the highlighting of the necessary command. For instance, he counts them for himself each time. Averaging occurs in real time and potentials are detected. Of course, highlighting unneeded commands will result in sensory responses alone, While highlighting the desired command that the patient has picked, a P300 wave is produced, which is detected by the classifier. Because the P300's amplitude is relatively large, from 2 to 5 highlights could be sufficient to choose the desired command. And the device starts. The chair moves in the selected direction, or the letter of choice shows up in the field. In the case of a typing device, the patient is presented with a screen displaying a matrix of letters and symbols. The patient selects a letter he wants to type and waits for the letters to light up. Rows and columns are highlighted one by one. The patient notices the sign every time it's highlighted. For instance, counts each highlight to himself. If the participant stays focused on the task and is not distracted, P300 appears each time the desired letter is lit up, and the interface using the intersection of rows and columns finds the letter and enters it into the field. Typing is quite fast when the classifier is correctly set up. This technology is crucial for those with disabilities who are unable to move freely or have limited vocal capability. For example, this technology is used in the communication system NeuroChat. Another practical task that the P300 can help us with is determining which of the watched videos captures the participant's attention the most. The auditory version of the P300 paradigm will serve as best for this. The task will be standard. The participant will have to detect rare target stimuli and press a button when they appear. At the same time, he will watch different videos. If the video is not interesting, the test taker will be completely focused on the P300 task. He'll perform well and will get a large positive wave when the responses will be averaged. If the video clip captures the participant's attention, then the attention resources are insufficient to do both tasks. There are omissions, not all target stimuli are marked, and the P300's amplitude is decreasing. This is how the P300 decrease allows us to objectively assess which of the videos piqued our participant's interest and drew his attention. The P300 is frequently used in neuromarketing research for a variety of methods. It should be noted that P300 varies according to age. The P300 latency increases and amplitude decreases with physiological aging. That is the reason for age to be considered in research and for uniform age groups of participants to be formed. Furthermore, the normative database is vital for clinical research because the P300 changes in different diseases. It can be used to detect early indications of Alzheimer's disease, autism spectrum disorders, and schizophrenia. To evaluate Alzheimer's disease impairment, they first employed the P300 paradigm, in which patients were required to count rare target stimuli. However, the paradigm in which the appearance of the target stimuli must be marked by pushing a button proved to be more effective because, in this case, only those epochs in which the patient correctly responded to the appearance of stimuli can be analyzed. Such studies have revealed that P300 changes dramatically in Alzheimer's patients. P300 amplitude decreases. It is especially clear in relatively simple tasks. And P300 latency tends to increase. The P300 paradigm is often used to assess impairment in autism spectrum disorders. However, the data obtained for autism is quite inconsistent. The main causes of this disparity are dissimilar paradigms and experimental methods used by the researchers, as well as the small sample sizes. The auditory form of the P300 test is the most commonly used type of testing for autism. The selection of this test is related to the disorder's auditory information processing deviations. The most significant findings were observed in the amplitude of the later subcomponent. The amplitude of the P3B in patients with autism spectrum disorders is lower than in neurotypical participants of the control group. When testing patients with schizophrenia, auditory version of the P300 test is typically used. As in autism, it gives good results. And most of the patients have a reduced amplitude of P300 in this paradigm. P300 is one of the neurophysiological biomarker associated with attack-like progressive form of schizophrenia. P3B amplitudes in particular can be greatly affected by the patient's clinical status. During the remission period, the amplitude of this component normalizes and reduces before the psychosis onset. Thus, assessment of P300 abnormalities in at-risk individuals may improve clinical prediction and clarify the pathogenesis of schizophrenia. In the first lecture, we learned in detail how to set up electrodes to record the electroencephalogram and event-related potentials. So let's just quickly go through the basic steps. We begin by selecting proper textile helmet, choosing the right size, placing the helmet on the participant's head, and fixing it with the chin rest. The hair is then moved from the areas where the electrodes will be placed. The skin is degreased with alcohol and scrubbed with an abrasive scrub. In particular, the skin around the area where the grounding electrode will be placed needs to be properly treated. Now, using a syringe, squeeze a portion of conductive gel into the fixation rings, install the electrodes, and connect them to the amplifier. We'll install 12 electrodes, including 9 active electrodes, 2 reference ear electrodes, and 1 grounding electrode. The software allows us to register P300 in a variety of testing scenarios. Depending on what scenario we choose, we can present either visual or auditory stimuli. All of these scenarios are in the PSS Neurovisor module. If we open a list of possible scenarios, the tests we require will be at the top of the list, denoted by VP300. These will be visual P300, visual stimulation tests, with visual stimuli such as squares at the top or bottom of the screen. It can be images of buildings and people. It can be geometric shapes that use not only the standard and target stimuli, but also a distractor stimulus. These tests can be delivered in a simplified manner when the duration of the presented stimuli is increased. We will employ an auditory variant of the test today. It will be scenario AP300 with audio stimulation, with tones serving as the standard and target stimuli. A standard stimulus of a lower tone will be presented more frequently, approximately 80% of the trials, whereas a rare target stimulus, provided only 20% of the trials, will be higher and will require a specific response from our research participant. When the target stimulus is presented, the remote button must be pressed. Before we proceed with registration, let us have a look at the settings in the selected scenario. You can verify which calculation points will be used on the Calculation tab. They will be selected by default during the selection of event-related potentials and will mark those components that we will pay attention to. You can also change the amplitude threshold of the artifacts here, as well as the calculation segment. This will be the epoch of analysis that we will use when selecting the responses received. It's 200 milliseconds before the stimulus delivery that will be used to correct the baseline, and 800 milliseconds that will include the epoch of analysis we require with all the components selected, both evoked response and potential associated with the P300 events. You can also set a random stimulus delay here and modify the button's confidence interval. You can choose the necessary detector scheme on the setup page. By default, a monopolar electrode scheme with 9 F3 FZ F4, C3 CZ C4, P3 PZ P4, and reference ear clips electrodes will be used. Finally, on the fourth tab, Filters, you may set the necessary passband. If you click on the drop-down menu, you can select the required value. To register the P300, we will set the high-pass filter to a value of 1600ths of a hertz, which will be enough not to reduce the amplitude of a quite slow potential. The low-pass filter will be set to 30 Hz. Before you start registration, you need also to choose the volume of the beeping that is comfortable for our participant. This can be changed and checked. Once everything is ready, you can access our test's start window. We can see the selected lead layout, and now it's important to establish a satisfactory subelectrode resistance so that all the electrodes installed are marked green on the screen. This indicates we'll have good contact and can proceed to registration. After you've set up the electrodes and adjusted the volume of the sound waves, you can begin the registration process. We are currently in the window that displays all of the leads in which the electroencephalogram is recorded. Our participant will be requested to go through training before the main experiment begins. The sound signals will be played in order. First the low tone, then the high tone, the high tone, the low tone. The participant's task at this stage is to learn to differentiate these sound tones and to hit the button only when the higher tone is presented. It will become the target one later in the experiment, will appear rarely, and will only require a response. So let's start the training. The patient's screen displays the relevant instruction. If our participant is ready to begin, we start the training. A vertical line marks the appearance of each stimulus. As you can see, no response is necessary for one stimulus, and there is no marking. However, for the following stimulus, there is a vertical marking indicating that the button has been pressed. The training is now complete. We can tell since the timeline on the screen changed its color. A stimulus was presented 10 times. The next stage is our experiment, which will contain 200 sound stimuli presentations. Only 1/5 of these will be given to the target stimuli. If the study participant has grasped everything, completed the task correctly, and pressed the button correctly, we can move on to the main experiment. Now, standard stimuli will appear considerably more often. They will not require a response, and they will be marked with single vertical lines, followed by the absence of a second mark, indicating that the button has been pressed. And only when the target, rarer stimulus appears does a second mark appear. It is the mark of hitting the left button on the patient's remote. This means our participant is carrying out his task. We can now switch to the averaged responses mode to see how the potentials are detected. Responses originating when a standard stimulus is delivered will be represented with green lines, as they do not require any response in the form of pressing a button, and we will just monitor auditory evoked potentials, which will be sensory responses, while at the appearance of the target stimulus, represented here by an orange line. In addition to the auditory sensory responses, we may also notice a positive potential deviation that occur in the first 200 milliseconds. This positive potential deviation will become more pronounced as the number of averaged epochs rises. Currently, their number is rather small, and we can use only 9 analysis epochs with 9 averages. It is yet insufficient to effectively detect the evoked response. Naturally, as the number of averaging epochs rises, the event-related component of the P300 will begin to stand out more and more. We can already observe a distinction between the green and orange curves. Note that more than 60 stimuli out of 200 were presented. Here we can see the complete duration of our experiment. If necessary, we can interrupt at any time. You can always hit pause to temporarily stop the presentation of stimuli. In addition, if necessary, we can double the number of stimuli presented. After averaging 18 responses for the target stimulus, it is now crystal evident that, in contrast to the green curve representing the evoked response to the standard stimulus, a large positive deviation takes place considerably later than the sensory response that comes before it. As you can see, it is extremely well represented in the case of a rare target stimulus. This is the same positive set that we discussed, the P300. The closer we get to the end of the experiment, the less residual noise there will be in the responses and the better these curves will be expressed, making it easier to recognize all the changes. During registration, we can also see what the response time was when pressing the button. Here, the most recent response, the average response of the participant are displayed. We may switch to the electroencephalogram registration mode anytime to check if the markings for the standard stimulus, the target stimulus, and button pushes appear. And yes, it's okay, everything is visible. So, controlling the experiment, we are awaiting its completion. After the test is finished, we can read the PDF report, which includes several pages. Here is the name of the test, indicating the instruction that our participant received. The percentage of standard stimuli, frequent stimuli, and rare stimuli is also indicated. We can see the names of expected wave responses that were preset in the scenario settings. Then we have a summary graph of all waveform responses and a summary bar chart of patient responses. This bar chart displays the distribution of response times of the button clicks. You can see that our participant did not make a single mistake. 100% of all target stimuli were marked correctly. Here you can see the average response time. The next page displays the registration parameters, and you can also note the resulting wave responses and amplitude maps that depict the topographic distribution of each component. A separate page displays the averaged potentials for all of the leads we used. Here, the evoked response to the standard stimulus is shown in green, while the evoked response to the target stimulus is shown in orange. It is obvious that, in contrast to the response to the standard auditory stimulus, a strong positive response is generated here. A difference curve is indicated in black, which is created by subtracting the potential acquired by averaging on the target stimulus from the potential obtained by averaging on the standard stimulus. This difference curve clearly shows the key differences between these responses. Finally, on the report's concluding page, there is a sample electroencephalogram with the marks of the provided stimuli. By clicking the More Details option, we are sent to the registered electroencephalogram, which has color markers. The green markers correspond to epochs when standard stimuli were provided, and the orange markers represent epochs when rare target stimuli were presented. It should be noted that the presence of each stimulus is marked by a distinct gray marker, and in the case of the standard stimuli, there are no more ones following it, as the stimuli did not require any response from our participant. While when the target stimulus, the rare stimulus, appears, our participant presses the button. An additional marker in our report indicates that this pressing was done on the left button. In other words, everything was done correctly. We can now switch to the mode of averaged potentials and responses and see how they looked for each lead. We can enlarge one of the graphs in the drop-down menu by right-clicking on it. For example, one of the leads we require. This time, pay close attention to the fact that a green line indicates the location of the evoked responses to a standard stimulus. We can see how many averages were used to highlight this response here. The responses to the target stimuli, on the other hand, will be highlighted in orange. Here, there will be substantially less averages. It should be noted that each participant's latency of the chosen components can vary, and we have the option of changing the specified default points in the settings manually. To do this, we may use the left mouse button to select the component we want and drag it to the maximum value of the desired component, and this value will be locked. Then we can repeat the process with other components. We'll now edit the peak latency for the P300 component. In this participant, it will have a greater value for 38 milliseconds more. And then we save our changes. Simply closing the window will suffice. These markers will be shifted in all leads. In addition to the opportunity to change all of our calculation points, we can also create amplitude maps for each of the components. To do so, simply double-click the left mouse button on the relevant component. First of all, we'll be interested in the topography of P300, and when you click, the corresponding color scheme appears with all the leads that we used highlighted. The color denotes the potential's negative and positive deviations. If the potential is negative, it is in blue section of the scale. Because we are dealing with a positive component, P300, all of the available color markers are in the red part of the scale. They are rather large. P300's amplitude is over 30 microvolts, and we can see that they're quite evenly distributed across the scalp. When we finish reviewing our data, we must make sure to save these changes by confirming this, and these changes will be reflected in the PDF report. So we have learned how to register and detect the P300 potential and discovered that it is an indicator of attention targeted at highlighting relevant events. P300 can be used for a general assessment of cognitive ability, as well as for the investigation of attention processes and working memory. P300 analysis can be used to diagnose and monitor a variety of diseases characterized by memory and attention impairments.